In this video, I'd like to finish Chapter 15 by talking about buffer solutions. As we discussed in an earlier video, a buffer solution is made up of a weak acid and its conjugate base, or a weak base and its conjugate acid in solution, or more generally speaking, as we said, a weak acid-base conjugate pair that are present in similar concentrations. A buffer solution resists change in pH when you add external strong acid or strong base, meaning the change in pH is small. And it does so by neutralizing the excess acid or base added. So for example, if strong acid is added, the basic component neutralizes it to form some of the acidic component, whereas if strong base is added, the acidic component neutralizes it to form water plus the basic component. In either case, as long as you're not adding too much excess strong acid or strong base, the pH remains relatively stable. We can prepare a buffer solution in one of three ways. We can simply mix in solution appropriate quantities of the acidic component and the basic component, which we've previously calculated. Or we could partially neutralize a solution of the weak acid with a strong base, generating a mixture of both the acidic component and the basic component. Or we could partially neutralize a solution of the weak base by adding strong acid, generating the conjugate acid plus some of the basic components. So here's what I expect you to be able to do, and that is the following. Calculate the pH of a buffer solution given the concentrations of the acidic component, the basic component, and Ka or Kb. Choose the appropriate weak acid or base and calculate the quantities of reactants needed to make a specified volume of a buffer of specified total concentration and specified pH using any of those methods. And for the rest of this video, I'm simply going to take you through several examples of this. Now, here's one important point. Cannot emphasize this enough. Remember the titration curve. The whole reason we covered 15.4 and 15.5 first is because I think thinking about buffers in terms of a particular region on the weak acid strong base titration curve makes a lot more sense. So in our lab experiment, we took acetic acid and we reacted it with strong base, sodium hydroxide, to form acetate plus water. This is what our titration curve looked like. We started at pH of around 2 or 3, went up quickly, leveled off, and then rose once we passed the equivalence point. And remember, at our initial volume, the main species present was HA, the weak acid, but at the equivalence point, right here where the pH is changing most rapidly, our most important species present was A-, the conjugate base. Here at the half titration point, you'll recall, is where the concentration of remaining acetic acid is equal to the concentration of acetate anion that we produced. And at this point, pH is equal to pKa. We said that is the center of the buffer region being the space around the half titration point where the pH is relatively stable. That's where we're going to be in every problem in this section, in the buffer region where the concentrations of the acidic component and the basic component are comparable. So let's do some problems. Here we calculate the pH of a buffer solution prepared by dissolving specified quantities of acetic acid and its conjugate base, sodium acetate, in enough water to make a specified volume. So you're given the masses of the acidic component and the basic component. You are given Ka for the weak acid. So we're simply going to take masses, convert those into concentrations, and then by using the Ka expression, calculate the equilibrium concentration of hydrogen ion, from which we calculate the pH. So let's begin simply by calculating our concentrations. Notice that a common abbreviation for acetic acid is HOAC, OAC being an abbreviation for the acetate group, and I'll be using that frequently. So our concentration of acetic acid we'll take by taking the mass of acetic acid, dividing by its molar mass, dividing by the final volume, 0.100 liters, to give us 0.260 molar acetic acid. Our concentration of acetate anion we'll calculate by dividing the mass of sodium acetate by its molar mass, converting the concentration by dividing by the volume to give us 0.245 molar acetate anion, which I'll abbreviate as OAC minus. As you can see, the concentrations of the acidic component and basic component are fairly close to each other, which means we are right smack dab in the buffer region, fairly close to pKa. Now, to calculate the equilibrium concentration of hydrogen ion, we will simply use the Ka expression. And we will consider the equilibrium ionization of acetic acid to produce the hydrogen ion and the acetate anion. Always a good idea to write out the equilibrium for which you're writing an equilibrium expression. Okay. And I'll rearrange this to isolate the hydrogen ion concentration. That's simply equal to Ka times the concentration of acetic acid divided by the concentration of acetate. Now you may be asking yourselves, where's the ice table? Where's my plus x and minus x? Well, as we learned at the beginning of this unit, this is a common ion effect problem. We have substantial concentrations of both the weak acid and the conjugate base. As we said before, any subsequent ionization is always going to be negligible. X is always so small as to be irrelevant, so we do not need to worry about it. We can always make the simplifying approximation. So my hydrogen ion concentration, I'll simply plug in. Ka is 1.8 times 10 to the negative fifth. And I'll plug in my concentrations of acetic acid and acetate. And I get a value of 1.9 times 10 to the negative fifth molar for my hydrogen ion concentration. And my pH is the negative base 10 logarithm of that, which is 4.72. Now, we began this problem by noting that because the concentrations of the acidic and basic component are similar, we should be close to the half titration point, which means pH should be very close to pKa. Well, let's just calculate pKa to see what that is. pKa, we said, is the negative base 10 logarithm of Ka, which is the negative base 10 logarithm of 1.8 times 10 to the negative fifth, which is 4.74. That makes perfect sense. The pH in this buffer is very close to pKa, which means we're right in the center of the buffer region. And furthermore, the fact that the pH is a little bit lower than pKa is consistent with the fact that our concentration of the acidic component is a little bit higher than the concentration of the basic component, which means on the titration curve, we're a little bit to the left of the half titration point at a slightly lower pH. It all makes perfect sense. So let's do another slightly more complicated example of how we calculate. Oh, before we get to that, let's move on to something that's actually a quite convenient abbreviation, and that is something that's called the Henderson-Hasselbalch equation. This is not required. If this makes sense to you and is convenient, use it. If not, use the Ka expression. So, if I consider the weak acid ionization of Ha, I can rearrange to isolate the hydrogen ion concentration as we did before, Ka times Ha over A minus. If I take the negative base 10 logarithm of both sides, I get this expression. If I separate out on the right-hand side negative log of Ka plus the negative log of Ha over A minus, well, I don't like that negative plus negative log, so let's do this. Let's do negative log of H plus equals negative log of Ka plus the base 10 logarithm of the basic component over the acidic component. So I inverted the ratio and changed the sign. Well, now I can simplify this because negative log of H plus is simply pH, negative log of Ka is simply pKa, plus the logarithm of the ratio of the basic component to the acidic component. This equation, as I said, called the Henderson-Hasselbalch equation, is essentially the logarithmic version of the Ka expression, and sometimes it's quite useful in performing buffer calculations. Again, if you like it, use it. If you don't, you can always use the Ka expression. So let's move on to our next example. Here we're making a buffer solution by partially neutralizing a solution of a weak acid, namely the dihydrogen phosphate anion. I'm given the initial volume and molarity of my weak acid solution, and I'm given the volume and molarity of strong base I'm adding. That will allow me to calculate the concentrations of the acidic and basic component, from which I can calculate Ka. Okay, now, it's important to remember that problems like this are a two-step problem. It is a stoichiometry problem followed by the equilibrium problem. Now, let's first consider the reaction that is taking place. Again, this is not the equilibrium. This is the chemical reaction that's taking place to produce our buffer. We are starting with a solution of potassium dihydrogen phosphate, which contains the dihydrogen phosphate anion. And we are adding potassium hydroxide, a strong base, to it to generate water plus the hydrogen phosphate dianion, HPO4 2-. And we're assuming that this goes all the way. I'm going to simplify this by writing it as HA plus OH minus goes to H2O plus A minus, keeping in mind what HA and A minus actually are. So let's break this apart into the two steps. Step number 1 is stoichiometry. I'm going to calculate how many moles of each reaction component I start with, and then I'm going to calculate the change in moles based on the neutralization reaction we just wrote at the top. So our initial moles of HA are equal to the molarity times volume, 1.83 moles per liter times 0.0250 liters equals 0.0458 moles of HA. And our initial moles of hydroxide are equal to 1.57 molar potassium hydroxide times the 15 milliliters we added, or 0.0236 moles of OH minus. As we can see, hydroxide is the limiting reactant. That means that after the reaction takes place, I will still have some of the weak acid component left, but I will have converted some of it into moles of the basic component. Now, to help us with the stoichiometry calculations, we can use a table that is similar to the ICE table, but different in important ways. So let's start by listing the moles of each component, HA, OH minus, and A minus. I'm going to list the initial moles, the moles that react, and the final number of moles present. It's not an ICE table. Yes, it's an earth table. So 0.0458 moles of the acidic component, 0.0236 moles of hydroxide, 0 moles of the conjugate base. I'll subtract the moles of hydroxide and add that, because that's equal to the number of moles of the basic component produced, to give me 0.0222 moles of the acidic component left, approximately 0 moles of hydroxide left, and 0.0236 moles of A minus produced. Now, these are moles. Unlike an ICE table, an earth table uses moles, not molarities, so I'm going to convert these into concentrations by dividing by the volume of solution. What's the volume I divide by? The total volume, which is the volume of the acidic component I started with, plus the volume of base I added. What I'm essentially doing is a partial titration of the acidic component to generate a mixture of both the acidic component and basic component, which of course is a buffer. So I'll divide this by the volume to give me 0.555 molar acid plus 0.590 molar of the conjugate base. So, having completed the stoichiometry step, I've calculated the concentrations of weak acid component left and of basic components produced, and now I can move on to the second part, which is the equilibrium calculation. And for that, now that I have the concentrations and I have the relevant Ka value, I can either use the equilibrium expression or I can use the Henderson-Hasselbalch equation. Now, again, it's important to consider the equilibrium that we're dealing with. And since we're starting with dihydrogen phosphate as our weak acid for which Ka is given, let's consider our equilibrium ionization to be dihydrogen phosphate in equilibrium with H plus hydrogen phosphate. for which Ka we said is 6.2 times 10 to the negative 8. Sorry. Well, I kind of like the Henderson-Hasselbalch equation, so let's use that. pH equals pKa plus the logarithm of the ratio of the basic component to the acidic component. pKa is negative logarithm of Ka, 6.2 times 10 to the negative 8, plus the base 10 logarithm of the ratio of the concentration of the basic component, 0.590 molar, to that of the acidic component, 0.555 molar. Let's calculate these just to see what these quantities are. This is equal to 7.21 plus 0.0265, or my pH equals 7.23. Again, the pH is fairly close to pKa, indicating that we are close to the center of the buffer region. Okay. Now, in this problem, we are going to make our buffer by combining quantities of the acidic component and the basic component, and we are going to calculate how much of each we need with the following stipulations. We are specifying the volume of the buffer solution, we are specifying the desired pH of the buffer solution, and we are specifying the total concentration of the acidic component and basic component. Those constraints will let us determine the masses of the acidic component and the basic component we need to measure out to make our buffer. So let's begin by considering the ionization equilibrium. Hypochlorous acid ionizes to form the hydrogen ion and the hypochlorite ion. Ka equals 3.5 times 10 to the negative 8. Let's go ahead and calculate pKa. It's the negative logarithm of that, or 7.46. That might come in handy. And let's just list our constraints in this problem. pH equals 8.00. Notice that we're trying to make a buffer for which the pH is fairly close to pKa. That is always the case. If you know the pH of the buffer you're trying to make, you choose a weak acid that has a pKa value fairly close to that pH, so the concentrations of the acidic component and the basic component are close to each other. We also have the constraint that the sum of the concentrations of hypochlorous acid and hypochlorite are equal to a specified value, in this case 0.500 molar, and our volume is equal to 0.2500 liters. So, what we're going to do here is the following. We're going to use the pH and the pKa to calculate the desired ratio of the basic component to the acidic component. And you can use either the Ka expression or the Henderson-Hasselbalch equation. And there we are going to use the total concentration to calculate the desired concentrations of the acidic component and the basic component. And then for each of those, we're going to use the concentration and volume to calculate the moles of hypochlorous acid and hypochlorite, and from that we will calculate the masses of each reactant we need. So, let's begin. For step number 1, I'm going to begin with the Henderson-Hasselbalch equation. pH equals pKa plus the logarithm of the ratio of hypochlorite to hypochlorous acid. I'll rearrange that to obtain the ratio of hypochlorite to hypochlorous acid. That's equal to 10 to the pH minus pKa. Notice I subtracted pKa from both sides, and then I exponentiated both sides. That is, I raised 10 to the power of both sides. I can now plug in 10 to the desired pH minus pKa of the acid equals 10 to the 0.54 equals 3.47. So that tells me that in order to obtain the pH I want with this particular weak acid, I must have a conjugate base to acid ratio of 3.47. Okay? So I can rearrange that to give me the hypochlorite concentration is equal to 3.47 times that of the hypochlorous acid concentration. Well, that looks like one equation and one unknown. How am I going to solve for each one independently? Aha! I have another equation. It's the one right up here, which is that the sum of the concentrations of hypochlorite plus hypochlorite hypochlorous acid is equal to 0.500, which is the total concentration I specified at the beginning of the problem. So now it's just algebra to isolate each of those separately. So hypochlorite equals 3.47 times the total concentration minus the concentration of hypochlorite is equal to 1.74 minus 3.47 times the concentration of hypochlorite, or 4.47 times the concentration of hypochlorite equals 1.74. And solving for the hypochlorite concentration, I get a value of 0.389 moles per liter. We probably only get 2 sig figs in this, but I'm going to cheat here. Hope you don't mind. And now, the concentration of hypochlorous acid is equal to the total concentration I specified, 0.500 molar, minus the concentration of hypochlorite I just calculated, or 0.111 molar. Okay? So, using the desired pH, pKa for this acid, and the total concentration of acidic and basic component, I've solved separately for the concentrations of hypochlorite and hypochlorous acid. That will give me a pH of 8.00. And if you don't believe me, you can plug them back into the Henderson-Hasselbalch equation, and you'll get 8.00. So now all that remains is to calculate the masses of each component that will give me those concentrations. So my mass of potassium hypochlorite equals the concentration times the volume times the molar mass, or 8.81 grams of potassium hypochlorite, and the mass of hypochlorous acid needed to form this buffer is the concentration of hypochlorite we just calculated we need, times the total volume of the buffer, times the molar mass of hypochlorous acid, or 1.46 grams of hypochlorous acid. So that's an example of how we calculate the masses of the acidic and basic components needed to make a specified volume of a buffer with a specified pH. I'm going to break this into 2 parts, so in the next part of this video, we'll do a couple more examples, then we'll talk about buffer capacity.